Okay, let's get started. Today we're going to switch gears mainly from talking about regression, which is really about predicting real valued functions, to talking about classification, which is about predicting one of some number of discrete values for a function. In particular, we're going to talk first just generally about classification and about, as a motivating application, we're going to use understanding electricity in buildings and how can we analyze electrical signal of a building, say from a smart meter or something like this, to understand what's going on inside the building itself. I'll talk then a little bit more formally about loss functions and how we define loss functions in classification. This sort of way of defining loss functions actually lets us solve or formulate lots of classification problems in a very similar way as we did with the regression problems. So we have a very similar formulation of the problem, even if the actual solution method, at least when you can solve it, things like least squares, we can solve it analytically, it's a little bit different. But when we have YALMIP, it actually ends up being very, very similar how you solve these things. I'll take a little digression to talk about Newton's method. And Newton's method is a way of solving certain problems, certain classification problems that are differentiable but don't have an analytical solution like least squares does. And we'll talk just briefly about nonlinear methods because the extension there is actually pretty much identical to that for regression. Just to finish up from last time though, I was a little bit, I think we were running a little bit late by the end, so I just wanted to highlight from the big picture what we did with kernels last time. There was sort of a lot of stuff that we covered last time talking about kernels, right? But I think from a high picture, the idea is kernels let us use these high-dimensional feature vectors that we couldn't even compute or store in memory without ever actually computing them, right? We just have this kernel function which computes inner products in this high-dimensional space. And we showed here we could essentially rewrite all our algorithms in terms of these inner products. But the cool thing is that when it actually comes down to the code in some sense, it pretty much looks very similar, right? So you have your solution here, you're solving for the alphas instead of for the thetas, and you have a kernel matrix here instead of your phi transpose phi matrix. But really the solution ends up being similar techniques you can get, at least for the least squares case, to compute the solution. And computing a kernel, this just also shows some code for computing the kernel itself. This would be computing a polynomial kernel right there in one little line. Compute the polynomial kernel, the inner product between all the different feature vectors, all the different inputs. And this is the same thing for a Gaussian kernel. So this code would likely be useful for your homework, for example, and you're welcome to just kind of use this code in the homework. I think that these things become a lot more clear once you do the homeworks and play around with them a little bit, because it really is the case that you can do this exact same thing here and you get something that looks just like what you would do in the case where you constructed the feature vectors explicitly. So this graph again just shows for, I think these are some polynomial fits and RBF fits. These two are polynomials here, different degrees. These two are RBFs with different bandwidth. You get something very similar, as you would expect, right, to what happened when you constructed them explicitly, where you can get overfitting, but you can also get very nice fits to these functions. This is all without ever actually computing these feature vectors. And then finally, the last thing was that you can apply this. I think one of the 830 problem sets or problems actually asks you to apply kernels directly to the absolute loss formulation. But you can apply this and asks you to actually write out this whole optimization problem. But the point is you can apply this to other loss functions and really a lot of other situations. The key transformation really is just the substitution here, saying that theta equals the features transpose times alphas. And essentially, if you take a linear classifier or any sort of classifier that has this linear in the features, you can usually plug this right in, and you'll get some cancellations, and what will pop out is the kernel matrix, and you get a problem formulated in kernel form. So again, this is not something that you will get immediately without any practice. The idea of the homework is to actually kind of drill these things in, but hopefully it does emphasize what's really powerful about these things and just why they have been so popular in machine learning in the last 15 years or so. For example, people name algorithms certain things, like if you use deadband loss, which is that loss that's 0 for a while and then slopes upward. If you use that in conjunction with kernels, people call that a support vector regression, for various reasons that are kind of more historical than anything else. But a lot of algorithms in machine learning can actually be formulated in this kind of framework here. Okay, so that was the big picture I wanted to say. There weren't really time for questions at the end of class last time, so are there any broad questions about kernels? Maybe I should look at the homework too and kind of get some idea about what these different concepts are. None, okay. Y'all understand it perfectly, kernels. Oh, you will see. Okay, so let's move on to the second topic, which is classification. Third. Second, third, I don't know. Next topic. All right, and as a way of motivating this, just the definition is, again, remember, regression, we assume that our outputs yi were real values, right? So we want to predict the peak demand from the temperature. That is a real valued function. Because you want to predict the actual number, not just some discrete set. Classification really is about things that don't have that form. Settings where, rather than predicting a real valued number, you want to predict some discrete set. For example, binary classification, that's two possibilities. This could just be -1 or 1 by convention, for essentially no or yes, the answer to something, for example. And why would you want to do this? Well, it turns out that lots of questions we might want to ask in energy domains, but in a lot of domains, really do have yes or no answers, right? So they are fundamentally things with yes or no answers. We shouldn't try to predict something real valued. We should try to predict something that's a yes/no answer. For example, we talked about, this is sort of a kind of subtly different example here, but we talked about predicting peak demand, but maybe all that we really care about, in some sense, and this is hypothetical here, but maybe all that we might care about is whether or not peak demand was going to be higher than some threshold, right? Because that sort of determines, do we have to schedule certain generators on or off? Maybe there's a big product cutoff point that really makes things differently priced in our electric grid. So maybe we just want to ask the question, is it going to be higher than some threshold, say 2 gigawatts tomorrow? And that's be yes or no, right? Because what we care about there isn't, what we're saying is we don't care about kind of getting the accuracy very, very good when you're predicting maybe it's 1.17 gigawatts. We just want to be really good at predicting that threshold. Is it going to be more than 2 gigawatts or not? And that's an okay example. It's not a great one because it's still sort of making a classification task out of a regression task in some sense. But there are a lot of other ones that sort of make a lot of sense directly in the energy domain. For example, will this wind turbine, if you look at some wind turbine, will it be operating at its maximum capacity in the next hour or so? Will the electric line become congested if we generate power according to some distribution over different generators? It's again a yes or no question, right? Is this line going to be congested? If it's not congested, it doesn't really matter. I mean, I guess there's a little bit more loss as you increase the current, but what really matters in some sense is this electrical line going to hit its maximum capacity? That's the yes or no question, and we should treat it as a yes or no question because really the yes or no answer to that is what matters here. Or something that we're going to talk about a lot more is classifying devices in a building. So I'll talk about this a lot more, but for example, if we see a device that's turned on in an electrical signal, what we might want to do is say, what is that device? And in general, that could be, maybe one of k different devices. That goes under the name of multi-class classification. But even in the yes or no sense, we could ask the question, we just saw some device turned on, say from the whole home meter, or maybe even from a plug meter plugged into that device. And the question is that device, say, a refrigerator or not? This can be very useful for sort of understanding of what's going on in a home. And actually a lot of the work I've done in recent years is not quite asking this kind of question, actually looking at it in a slightly different way, but talking about how do we analyze energy consumption in a building. Yeah? Well, that's the question. I'll get into exactly how I'll talk about that problem a lot more right now, but it's just the question. I'm just giving examples of questions that have yes or no answers, where you do care about the yes or no answer. Well, okay, so you might care about what the current of some device is, but you can measure that kind of directly, right? You just plug in a sensor, or you look at your meter, and it says this is consuming this much electricity. Yep, that's true. So that could be a problem. Are they going to have the exact same characteristics, both power-wise, temporally, and in terms of other characteristics of power? That becomes less likely then. So the question is, can you do this? And you can in a lot of cases. There actually are enough features to distinguish devices like a refrigerator to classify that against other devices. And I'll give an example right now coming up. And this last point is just the kind of point I was making up here, saying that sometimes even when we're kind of, in some sense, predicting a numerical quantity, what we really care about is still the answer to a yes-no question. Something like, is the peak demand going to be higher than 2 gigawatts? If that's a threshold for some reason, we might want to focus on asking that yes-no question versus trying to predict the exact numerical quantity. So that's sort of the broad idea that makes sense to everyone about what classification is. Okay. So I'm going to take a little detour now and talk about this problem of analyzing energy consumption in buildings. And I'll be kind of brief with the motivation here, because I want to get into the actual details of how we go about doing this. But I think the basic sense is that buildings consume a lot of electricity in the country. It's about 71% when you combine commercial and residential of our electricity goes into powering buildings. And that's lots of heating and cooling, and lots of things like lighting. And electronics becoming more and more a big part of that. And the question is, in some sense, if you're a building manager, it can often be very hard to know exactly where electricity is being consumed in your building, right? All you see is, for example, your monthly bill, or maybe you have a real-time power monitor, but it shows a lot of kind of spikes, and you don't really know what's going on. What's very useful for homeowners or building managers and like this is an actual breakdown of the different types of usage, say, by device. So if you could say this much power is going to your refrigerator, this much power is going to your air conditioner, etc., that can be very valuable for understanding your consumption and then using that to reduce it. So that's all I'm going to say about the motivation there. I think that a lot of people here actually work on similar problems. But if you want more, I can talk a lot about this particular domain at great length. So the question is then, how do we go about determining if what percentage of electricity, for example, is being used by a refrigerator? Or when the refrigerator is on in the building? How do you determine that? And it can be tricky, right? Because there are all these things like, well, the device might use the same amount of power as a refrigerator. What do you do with that? So the task I'm going to focus on here is automatically identifying what devices are from their power signal. And we're going to think here about looking at their individual power signal. In reality, very similar things can be used to figure out what's going on just from for example, a whole home or a whole building monitor, because you can still see sort of similar edges in your power signal. But here I'll just talk about, suppose we had a plug or a monitor on every single plug when we built the building, for example. But then we didn't go around and record what every single device was when we plugged it in, or maybe they move from plug to plug. Sometimes people will, plug a computer into an outlet one time and a different outlet another time, and you don't want to have them enter in a big database every time they do that. You just want to figure out from plug level measurements or individual device measurements what this device is. So is that sort of problem setting clear to everyone? I mean, it might become more concrete once I just show some of the examples. Actually, maybe let me just do that here. So here, for example, is a refrigerator. This is the power signal of a refrigerator over time. This is what you would get, for example, if you had smart outlets here and you were able to monitor just the power of this one refrigerator. Essentially happening is that there's some base level load, but it isn't very much. And then occasionally, every so often, the compressor comes on and sort of goes in this little pattern where maybe the resistance is a little bit lower at first. So it starts with a little spike there and then settles down to a steady state, and then the compressor turns off. Right? Refrigerators work by, they're not on all the time. Right? What they do is that they look at the temperature inside the fridge, and if it falls below or raises above a certain point, the compressor comes on. When the temperature, and then that cools the refrigerator. When they then cool down enough that it reaches kind of its minimum temperature, the compressor turns off and lets it warm back up inside. And maybe that'll happen quicker if you open it up. And for those that know this well, there's also things like a defrost cycle, which look a little different than this, but this is basically how a refrigerator works. So now the question is, we have one fridge that looks like this, and another one maybe looks like this. Maybe we have two different fridges, two different devices, and we want to just tell them apart. Right? We want to know, if I plug one of them into this outlet, which one of those two it is. This is very useful for things like, well, maybe one of these fridges, in fact one of them is using a lot less power than the other one. It's a newer model in this case. This one here, it uses more power sort of per time, or at any given time, but it's on for much less time. So if you could identify which refrigerator someone has, you might be able to give them advice about, hey, maybe you should buy a newer model, or something like this, right? So again, this is kind of a cartoon example here. So we're talking about just two refrigerators out of the entire universe of possible appliances. But intuitively, there is some value in being able to tell one device from another, right? Just by plugging it into an outlet and monitoring that power, without having to type into a database or look up the efficiency, things like that. Just figure out what it is. So look at these again. So this one is, the X's here are the same. And this one is one refrigerator, and this one's another one. So this one goes on for higher, uses more power when it's on, but stays on for less time. And that's this one ends up using a lot less power. All right, so this is great. We have this task now. We want to tell this apart from this. And I should say, these are sort of two characteristic examples of the refrigerator, but there's some randomness here too. They don't come on to the exact same power amount every time. They don't stay on for the exact same length every time. There's some variability there. And so you can't just, for example, write a program that would just look for an exact amount of power that one would consume. Now that should be a very bad program. You'll see shortly just how bad it would be. Okay, so we need some way of describing these refrigerators, right? I mean, this is a vector. We have a power reading for every second, so I guess you could call it a vector in 7,000, R to the 7,000, but that's a pretty bad way of describing things, right? We want to put some inputs into our machine learning method that kind of describe what this is. And one example of what we could do here would just be kind of obvious, right? It's the average power that these things consume when they're on. Let's describe, I mean, that looks like it might distinguish those two, right, in that last picture. Let's just figure out when they're on, which is a simple kind of threshold function in this case. They're above a certain amount, we'll just say they're on. And let's just take the average of the power of when it's on. Now this ignores a lot of things, of course, like this particular shape here, etc. But it's an intuitive thing, right? Let's just call the refrigerator the amount of power it consumes. So we do this for both the two appliances, and we get a figure that looks like this. Okay, let me describe what I mean here, because there's a lot of colors now. This, on the x-axis here, is the average power that the fridge consumes. All right, so that is this line for 2,000 or so examples of a refrigerator. So again, this point on this x-axis is just how high the power is. The y-axis here is our output. Remember, the output we said was going to be either 1 or -1, depending on which refrigerator we were talking about. So if we are talking about that first refrigerator, which uses going to be less power but stays on for longer, we're kind of in this range here of power, and the other one is in this range here, in terms of average power. And these kind of figures are a little bit odd to look at, but in some sense, this is exactly the kind of lines we had before, or exactly the kind of plots we had before with linear regression. Remember, our input is the power something consumes here now. And the output now, rather than being a real number, the output is just going to be 0 or sorry, -1 or 1. Yeah. Each dot is one observation of that refrigerator. So there is some randomness here. These things clearly don't use the same amount of power every time, as we can see from this. The two were actually right next to each other, so they just happen to have very similar times of day and all that kind of stuff. But each one of these is one time the refrigerator came on and then turned off. The idea is we want to be able to plug in a new fridge, see it come on one time, and say what that is, right? And this plot really, this figure here really is the same as we saw last time, in that we have our input on the x-axis and our output on the y-axis. Now, one thing we could do at this point is just run linear regression, right? Because even though they are discrete outputs, it doesn't really matter. I mean, we can still just map them to -1 and 1, and we just run regression. And what that kind of does is it just fits a line to that little function. Maybe a line is not the best thing to fit to that, as you might imagine, but it still could be kind of okay, right? Where you have a bunch of points here, a bunch of points there. This is our input, x. This is our output, y. Maybe a line like this would kind of work, and if it's bigger than 0, you just call it fridge 1. If it's less than 0, you call it fridge 2. Yeah, I'm just talking about the points when it's over some threshold. That's how I kind of classify on power. So really, I'm treating the feature as the power it uses when it's on. Now, you could also create a feature out of power it uses when it's off, or when the compressor is not on. That might also distinguish between different fridges. But for this example, it's just kind of it is not, and again, it's not the best way of doing it necessarily. I'm just looking at the power that it consumes when the compressor is on. So we could solve this, as I said, with linear regression. But sort of intuitively, this doesn't seem quite right? Because we're predicting something here that can go sort of take on any value, even though our output only takes on one of two different values. And even more than that, sort of our big problem with this is suppose you had one lone example, or actually one example that was, I could have in the video screen anymore, so I could have put it over here or something like that. Suppose you had one example that was way over here. So it uses a lot of power, and it is bridge 2. Now, this sort of is fine in some sense, right? This line here that we drew still worked fine. But if you use least squares, remember least squares tries to fit a line to the actual data points as well as it can. So what you'll get oftentimes is you'll get something that looks like this, where it tries to kind of hit this point a little bit better, and in doing so performs a lot worse on kind of the other points. Right? There's some sense in which we say, well, we don't really care about if we get something really good. We don't really want to care about the fact that we did really well on that in some sense. So this is why you might not want to think of these things just as regression problems, but might want to actually think in a different sense and talk about different loss functions you might think about for classification problems in particular. Does that make sense to everyone? Sort of the connections there between the regression case and why also it might not be the best idea to think of it just as a regression problem? Okay. So before going on to the more formal definitions here, I want to show one more figure, which is the case where we have two different inputs. So the feature I extracted here was just the mean power that we consume. But another thing that might be very valuable, and which, as you can sort of see, is a differentiating factor between these different fridges, is also the time that it's on for. So we can actually think about there being two inputs to our problem now. Both the power something consumes and the length of time, or the average power it consumes, and the length of time it consumes that for. This is easy for a fridge because they're kind of simple things. Like they just turn on and turn back off. It might be harder for other devices where they might vary more smoothly and things like this. But for a fridge, these are sort of two very natural features that describe the refrigerator. If you know anything about AC power, which we'll cover shortly, but this will all make sense shortly if it doesn't to you now. But another common feature people use is not just real power, which is how much power sort of the fridge is actually consuming, but also something called reactive power of the fridge, which is kind of hard to describe without giving too many definitions here, but it's kind of power that the fridge draws and then regenerates every single time power cycles through its waveform. Again, don't worry about that. We'll see it shortly, but when you talk about AC systems, that's power that oscillates, where the voltage oscillates back and forth. There's another kind of power that actually is sort of sucked up and then put back in the system every single time through. This is called reactive power, and different devices, just like they consume different amounts of real power, can also consume different amounts of reactive power. And that can also be a differentiating feature oftentimes for these devices. But we won't worry about that yet. We'll just talk about these things in terms of the power they consume, and when I say power here I mean real power, for those that know that terminology, and the duration that they're on for. And now I'm going to plot this same kind of picture. So this picture is a little bit redundant in some sense, right? Because there are only two possible outputs, and I'm coloring them differently here, but I'm also putting them on different points in the axis. And so it turns, for classification, actually is very nice. We can just code these things differently, different colors here, and actually show it in terms of two different inputs, where we have to have that kind of be a 3D graph, a little bit less intuitive for a regression case. But in the classification case, we can generate plots like this. So what this plot shows is these two different inputs I talked about before. I guess I'm kind of using inputs and features here a little bit imprecisely. I'll call them inputs because they are two different things that we are feeding into our algorithm. So on the x-axis, we're showing the power. So if we took this, ignore this axis and just kind of squeeze this down to what we saw before, that would be the plot you saw on the last slide. But I'm also now showing as the y-axis the other input feature, which in this case is duration, how long something's on for. And the z-axis here would be implicitly saying that these ones would be at the 1 level, this would be the -1 level. We don't really need to do that because they're different colors. So we can kind of view these ones being -1 and these ones being +1. All in a nice kind of figure here. And hopefully this also kind of helps to motivate exactly what's happening in terms of two different inputs here and making predictions based on more than just one input, that's two inputs now. And what linear classification does is, much like linear regression, it is just drawing a line through that picture and saying everything on one side of this line is one class, everything on the other side is a different class. That's, again, a linear classifier. And it's also not quite right to think of this as just a line. What's really happening here, which hopefully will be a little more concrete when I introduce notation, is we're actually fitting kind of a plane to this thing. And we're saying where that plane crosses your zero axis, that's the line that I'm drawing here. I'll clarify all that shortly, but just to make that clear. This is actually the classifier you get from what's called a support vector machine. Have people here heard of support vector machines? Just raise your hand if you've heard that word before. Okay. Some people know what it is or could implement it? Okay. So good. So now at the end of the class, you'll know how to implement a support vector machine too. Much simpler than you know how to, and much simpler than it's presented in a lot of cases, but you'll know how to do it for maybe small size examples. Okay, so now let's formalize our notation a little bit. As we did for regression, let's talk about classification now a little bit more formally. Everything really stays the same as it did for the regression case. And I won't bother writing it too much, except, remember, our input is n-dimensional. Call it xi, and there's m of these. It's exactly the same as before. Our output, the big difference now, is our output, rather than being real valued, for at least this binary classification task. And we'll talk about binary classification for this lecture. One of the homework assignments for the 8:30 is going to be about multi-class classification, but binary is sort of the simpler case, and the extensions are really pretty straightforward too, it turns out. So in the binary case, our two possible outputs corresponding to, say, yes or no, or fridge 1 or fridge 2, we're just calling these -1 and 1, just out of convention. Just as before, we have a feature mapping, which takes our inputs as input and outputs feature vectors of dimension k. So this is exactly the same as before. And we have, again, just as before, we have some model parameters, theta in our k. So we have k different model parameters. The big difference here, well, actually it's the same, but a difference is that our predicted output, since our outputs are -1 and 1, you would think, well, you should make predictions that are also -1 and 1. And that's true, sort of. But for convenience, I'm actually going to say our predicted output, remember y hat was our predictions, and y hat I was our predictions on the ith example. I'm going to say that's actually still a real valued number. So predictions we make here are still real valued, and they are still equal to theta transpose c of xi. With the intuition being that if y equals 1, yi equals +1, we want y hat I to be greater than 0. Okay, so we're making real valued predictions, but the sort of class of that prediction, in some sense, is just the sign of this real value prediction. And again, if yi equals -1, then we want y hat I be less than 0. Where you can use whatever notation you want, or whatever convention you want for this being equal to 0. Equal to 0 means you're kind of most unsure as you can be, right? It's like right in between -1 and 1. And the reason we do this, really, is so that a lot of our formalism for loss functions and for optimization carry over exactly as they did before. It really is identical from a high level, a lot of our formulations. So the important part, in some sense, for classification are these loss functions. And the loss function now is a function L, which takes as input a real value number, which is our prediction, and a true label, which is going to be 1 or -1. And that outputs, again, some loss that's 0, greater than or equal to 0. And again, this loss function basically measures how good our prediction is. Now, remember, this loss function takes as input our prediction, which is real valued, and the true label, which is discrete valued. So the simplest case, the simplest possible loss in some sense, is just to say, well, look, our predictions, when they're positive, we're sort of in effect predicting the label is +1. And when they're negative, we're kind of in effect predicting the label is -1. So let's just make a loss function that is equal to 0 when we get the label right, the sign here right, and equal to 1 if we get the sign wrong. That's kind of like the accuracy of our classifier, right? We just get a point if we get it sign right, or get 0 points because their points are bad here. If we get a sign right, and then we get penalized a point if we get the sign wrong. And one way of writing that is that this loss function here, well, it equals 0 if the true label is +1 and we're greater than 0, or if the true label is less than 1, true label equals -1 and our prediction is less than 0. Does that sort of, and we suffer loss 1 otherwise. So does that first one here make sense? Okay, so now it's sort of convenient oftentimes to write this in a little bit different form. What we're going to do instead is say, I'm just going to write this exact same thing. It's equal to 0 if the product of the true label and our prediction is greater than 0. And that will be the case here and there, right? Because these are both positive, the product will be positive. These are both negative, the product will also be positive. So we suffered 0 loss if this is positive. And here I guess I'm treating equals 0 as meaning you did a, if one of them is, prediction is 0, I guess here you do okay. And our loss is 1 if this product is negative. And you write to simplify this again, and just say we're just going to call this the indicator function of this product being negative. The indicator here just is a function that takes this condition inside, outputs 1 if it's true and 0 if it's false. Everyone's seen the annotation before of indicator functions? Okay, so the important thing here is that this loss function, it might seem kind of complex to write it like this, but really we can write it very compactly as just the indicator of some product of these two things. And really, part of why we're going to adopt this notation of having real valued inputs and real valued predictions and discrete valued true outputs is that it kind of makes it easy to write loss function in this kind of nice form here. An important way to think about this is to think about it in terms of a graph, right? So if we graph now, rather than as we did with classification, or sorry, as we did with regression, what we kind of graphed usually was the difference between y and y predicted, right? Here I'm going to graph the product of the true output times the prediction. And if this product is negative, we suffer loss 1. If it's positive, we suffer loss 0. This is a graph of this loss function, which we call 0-1 loss, or just accuracy sometimes. Don't know a lot of names, but 0-1 loss is probably the most common. This notation here makes sense to everyone. Okay. The problem with this loss function is that unlike our squared error, it can be very hard to optimize 0-1 loss. So remember, we talked about at the very beginning of this course convexity, or actually maybe not quite the beginning, but the first lecture, so we talked about convexity, right? And if functions were convex, if you could draw the function, take any 2 points, and the line between them lay above the function, right? Or above or on, I guess, above or on the function. So, though we didn't really discuss it formally here, informally, we said that convex problems are kind of in general easy to optimize, whereas non-convex functions can be very hard to optimize. And it turns out, as you can see from this, that 0-1 loss is a non-convex function. So 0-1 loss, right, has this, looks like this. And if you connect these 2 points here, does not lie above the function. And it turns out actually finding the parameters theta that would minimize this 0-1 loss over some big set of data, that is an NP-hard problem in general. So you can't unfortunately do it. Now for this reason, 0-1 loss oftentimes is kind of what you think you should care about, right? Because 0-1 loss, if you average it over a data set, that would just basically be, on average, are you right or wrong, which would essentially just be the accuracy of your classifier. So the accuracy, 0-1 loss essentially corresponds to accuracy when you're looking at a big data set. Again, unfortunately, it's hard to optimize. Maybe that's what we really care about, but we can't really solve it. So because of that, a whole bunch of other loss functions have emerged that kind of look like 0-1 loss, but which are convex. And actually, maybe, I think I have on the next slide just a graph of all these things. So maybe it'll be better to just view them first, and I'll give you the actual definition. So, to name a few, this is, again, this blue line here is 0-1 loss. The red line, which is 0 everywhere, and then at 1 goes up, and then increases linearly, that's called hinge loss. That is defined formally as the max of 1 minus this product and 0. So again, this graph here, so I'm just looking at hinge loss now. This graph here is showing the product of y and the prediction. I'll actually write it here. The hinge loss is the max of 0, max of 0 and 1 minus y hat I times yi. Actually, I'm just going to write it like this. Just forgetting about the subscripts there. The loss takes as sort of as input arbitrary prediction an arbitrary true output. So that's hinge loss. And hopefully that sort of corresponds to what, you can see why this graph corresponds to that. We just had this part here. It would be remember the x-axis here is this product here. So we just had this part, it would just be a line with an intercept at 1, which is a negative slope here. Then we're going to max it with 0, so that you never go below 0. So once it hits 0, it just stays at 0. As a little preview, a support vector machine just minimizes hinge loss, plus some regularization. That's all it is. Just classification minimizing hinge loss. That's what a support vector machine is. If you've seen it before, or in other classes, oftentimes it's described more from a geometric perspective in terms of, what the separating hyperplane does. And that's all true. It's a good way to look at it, but this is also true, and this is also what a support vector machine is. Another very common one is something called logistic loss. So that's a little trickier form here. What that is the loss function between taking in y hat and y is the log of 1 plus the exponent of this product here. And what that looks like is sort of like hinge loss, but kind of like a smooth version. The intercept's not quite at 1, but then it starts going linear at some point. Essentially, oops, back to this slide. So if this is very, very big negative, this term here will almost be just like this term here, almost just be e to the negative product here. Because the 1 won't really put much of a factor in if you start getting e really big. Take the log of that then, that's kind of like just this element here, approximately. So as this product here gets very negative, this becomes like a line. And as it becomes positive, this term here goes to 0. As this product becomes positive, e to the negative something big goes to 0. And so the log of that log of 1 plus that goes to 0 also. So you have something that looks very similar to the hinge loss here, but it's kind of smooth. It doesn't ever get to 0. It kind of always slowly goes. It's closer and closer, never quite there. And similarly, it never is quite linear going that way, but it's becoming pretty close to linear. This, if you use classification with this loss function, that's called logistic regression, which has been around a very, very long time. And again, those have other interpretations, namely a probabilistic interpretation for that method. But from an optimization standpoint, you can see it just as classification with this choice of loss function. And those are the differences between these different algorithms. So kind of funny here, right, is that hinge loss and logistic loss look pretty similar, right? And this is yet, 20 years of machine learning progress to go from one of these to the other ones, I guess. Support vector machines, right? Those are much more powerful than logistic regression. I'm kind of being tongue-in-cheek there, but these are very similar in a lot of ways, and they have similar properties in a lot of ways. And you can have other things. You can have things like you can just take the exponential here. That's also always going to be positive. Going to heavily penalize you from ever going negative. You can take the hinge loss and square it. There are lots of different possibilities you can have here for different loss functions, and they're all kind of approximations to the 0-1 loss. You might think it was a very bad approximation in some sense, but really this is kind of, and you can be a lot more formal here, but in some sense these are kind of the best convex approximations you can get to the 0-1 loss, right? If you want a convex function, which is something you can optimize, the problem is, right, so you want something that kind of is low. So again, this is y hat times y. You want some function that is low when you're over here, because that means you've classified it correctly. You kind of want this to be 0 in this region. you want something here that's kind of high, like 1, or even some arbitrary high number, maybe. The problem is, for things to be convex, if you increase it here to any point, if you have some increased point there, well, you have to be at least, wherever you want to call 0 here, you have to be at least, above some line that you would draw between these two things. The whole function has to lie above that. It could never go below that now, because then this would be a non-convex function. You could draw a line that was below the function. That doesn't make, if that doesn't make sense to you, don't worry. Essentially, even though these might not look very much like 0, 1 loss, they are, in the convex sense at least, some of the best approximations you can get to 0, 1 loss. At least in case of hinge loss, that's true. Logistic loss kind of also. These other ones less so, like exponential loss. That increases a whole lot as you get negative. But that's sort of a side note. Don't worry too much about that. Any questions here? Okay. So again, what I said last time was logistic regression is just that optimization problem we've been looking at this whole class, right? You're optimizing the loss over the sum of all examples, where you choose as your loss function the log, the logistic loss. Let me just write this out, actually. Remember, our basic optimization problem was that we wanted to minimize over our parameters theta the sum over all our examples, I equals 1 to m, of the loss between our predicted value and the true value. Right? So this was our optimization problem that we had for linear regression, for the different loss functions in regression, and it's exactly the same for classification. That's our problem. Also, just as before, we're going to take our prediction here as equal to theta transpose e xi. So now, at this point, we are exactly the same as the regression case. The only difference is that these yi's happen to actually be discrete here. So we need to use one of our classification loss functions. And if we take this and we plug in the logistic loss, which is, remember, logistic loss is 1 plus the exponential of this product here. So logistic regression. Theta, the sum, all our examples, of log 1 plus x negative, and negative it's yi times yi hat. But again, this yi hat is just equal to our prediction times theta transpose e xi. I have one more pencil there that I've run out of room for. So that is logistic regression. That's how you solve it. Oh, sorry, that's how you formulate it. Not quite solve it yet. Though, again, with our nice programs like YALMIP, you can just type this in to YALMIP and it will solve it. Now, it is important to know, we're not going to cover this. I'm actually doing in some sense, I'm talking very, very little about probability here at all in this course. I'm talking about machine learning without probability, which is, yeah, some people might think that's crazy. But it's important, and we're not going to cover just out of time. We're trying to cover this quite briefly. Obviously, it is a very, very important part of machine learning with probability. But though we won't cover it, one important thing to know is that there actually is a probabilistic interpretation for this logistic regression. And the basic idea is that you can think of it as kind of encoding the probability that your output is 1 given your input. If you haven't seen this sort of notation before, don't worry about it. But basically, under the assumption that this is how you model probabilities, so your probability of y given 1 equals 1 over some exponential here, and there's some justification for why you might want to do this as well, then this objective here is just maximizing the probability of your observed data. So that's just one interpretation of what this thing is doing, and probably the more typical interpretation of what we're doing here. But again, you can think of this just in terms of this loss function too. So from the standpoint of actually solving, I could minimize the 0 here, whatever theta. So from interpretation of actually solving this problem, you can think of it just as minimizing a loss function, as we did before. Now, as I said, a support vector machine is just, instead of logistic loss, you take the hinge loss as your objective. That's the only difference. You also typically add some regularization here. So remember, we before talked about regularizing the L2 norm of our weights parameters here, and you typically in support vector machines you do that as well. You add some regularization there. It's almost always formulated that way, very rarely without the regularization effect. If you do a Google search for support vector machine in the last 20 years or so of literature, you'll find so many examples. And really, logistic regression has been around for, I don't actually even know how long since it was around, but it's been actively solved for 50, 60 years at least. And so, this again being the progress we've made in all these years. So really, I think support vector machines came into their own because of their use with kernels. And there are some reasons why actually this loss function is very nice when you use kernels. And it's nice because you end up getting cases where your alphas are oftentimes, there's a lot of zeros in the alphas, so you don't have to store them all. Don't worry about that. The point is that this is a support vector machine, this is logistic regression, and they both fit into this framework of minimizing a loss function over all your data, plus maybe some regularization on your parameters. Okay. Questions? I guess I should just say it's also throughout the code for how you actually solve these things here. Again, we'll talk about a more detailed way in a second for solving one of these things. But if we're using our program, YALMIP, we'll just say, man, I keep putting n there instead of k. I gotta start putting k in those things. I keep trying to fix some, but I guess I used n at one point. So. But anyway, the formulation there is just, again, set up your parameters as you did before, minimize the loss function, and where here you're just taking the loss, just your y's times your predictions here. So as you did before, you can come up with a vector of all your predictions as this big matrix phi times your parameters theta. Y is a vector of all the true outputs. What this MATLAB code does is just compute all the predictions, multiply those element y's, dot product dot times means element y multiplication. Take the exponent, that takes the exponent of all of them individually, add 1, that adds 1 to all of them individually, take the log, all of them element-wise, and then the sum of those. So that is just this thing, sort of a convenient way of writing this in MATLAB. And same with the SVM. You just have the hinge loss here instead of the logistic loss. Yeah. This one. So you mean one that came here, for example, went to 0 here, and then came up? Yeah, you could do that. So the reason why they chose this location is that, for hinge loss at least, is that hinge loss with this choice of location is actually always bigger than 0-1 loss. It's an upper bound on 0-1 loss. And so if you compute the hinge loss, that will always be bigger than the 0-1 loss. So essentially, if you compute kind of like an accuracy with hinge loss, that will always be, you know, worse than your accuracy you get with a true 0-1 loss. And so a common theme in optimization is that if you find a function that you cannot optimize, you take sort of the lowest convex upper bound of that function. You optimize that instead. That's why they chose this location here. Now, logistic loss actually is not an upper bound on this. Logistic loss can be lower, in fact, than the 0-1 loss. And it's actually fine to shift this over. That's another loss, and that actually results with some, don't take this too literally, but an algorithm very much like that is what's called perceptron algorithm. So that perceptron algorithm actually uses a loss that essentially is this one exactly, where this starts at 0 here and goes up from there. So you can do that. You wouldn't want to shift it more than that, right? Because you wouldn't want to shift it too much this way, because then you start suffering high loss even if you get the right answer in some sense. If you shift it too much the other way, then you start getting 0 loss even though you got it wrong. So you probably wouldn't want to do that either. But these two choices, kind of anywhere in between here for the 0 point, would actually be reasonable. And the algorithms are pretty simple differences. They don't really perform that differently in some sense. The reason why this one's so popular again is because of this fact that it will in fact be an upper bound on the 0-1 loss. It just doesn't. Logistic loss, I mean, you could scale it and have it apply to that if you want to. Sometimes people do scale it. I mean, scaling, if you add a constant here, this won't affect your choice of parameters at all, right? You can add a constant and won't affect your choice of parameters. So you can. I think you have to scale it by some term like, log of 2 or something like that, right? So you can do that, but it just, there isn't that much need for it really. Okay, great. So this is code. This code right here is now you can code a support vector machine. Everyone knows how to, right? It's one line of MATLAB code. Again, using this fancy optimization package. But that's pretty nice. I mean, this is an algorithm that you see everywhere in machine learning. It's pretty nice to know that you can code it up in one line or two, and you'll do it for the homework. Not this one, but the next homework, you'll write a support vector machine. And it's right here, so it's not that hard. All right, so I want to take a little, I should just say here is the resulting boundary I showed before. When you do this, and again, now maybe this makes a little bit more sense. We have two inputs here, right? So what we actually get out from this classification, or from this prediction, is a linear function takes two inputs and outputs a real value number, our prediction, right? And what that prediction is actually, what that sort of surface looks like is actually kind of a plane through here, right? This thing will predict maybe, z equals whatever, y hat equals 1 here, and y hat equals -1 somewhere there, etc. So what I'm drawing in this line then is the place where that line crosses through the 0 value. This is that equation of that plane being equal to 0. And that's really where you go from predicting things being positive to being negative. And so that kind of encodes the decision boundary, because if you're going to ultimately make a decision, make an assignment, you'll just assign it to be the sign of that thing. If you do want to make a yes or no prediction eventually, even though our predictions kind of in the meantime internally are real valued, if you want to output a number and tell someone yes or no, you'll just take the sign of that number and output it. So this is the time where that sign goes from being positive to being negative. Or negative to positive. Sorry, I think actually this might have been positive and this might be negative for the first slide convention, but not that important. Okay? All right, so now I want to take a little digression and talk about how you might go about solving a function if you didn't, or solving one of these problems if you did not use YAML. Again, this is sort of why support vector machines, for example, have been a lot more than just that one line of code or just one loss function, is because when we actually talk about solving them, there's a lot you can do to get good solutions to this problem. YAML is great if you have a very small problem, say maybe 500 variables or something like this. It can work pretty well, and it does work very, very well oftentimes. But once you start getting really big, it starts slowing down a lot. And so, as we'll see in a second, in fact, for logistic regression here, if you solve it in YAML using this code I showed you before, that's really, really slow. It takes a really long time, even for a pretty simple example. Just the YAML functions are, for kind of technical reasons, it ends up not being very good at doing things like logs and exponents. Kind of internally has a hard time with those things. And so it ends up being quite slow to solve this problem like that using a general purpose library. SVMs are actually a little bit nicer, but still nowhere close to as nice as you can do if you were to write a custom piece of code just to solve that one optimization problem. So how might you go about solving an optimization problem? It ends up being hard for something like an SVM because for the same reason we have with the absolute loss, the loss is non-differentiable. You have kind of kinks in the loss function. Here you get a kink at 0 or at 1, where the function went from being 0 to being a slope upward. And so it can kind of be hard what you do is you can write it as in this case, a quadratic program, and you'll cover a little bit about quadratic programs in the homework. But you can write it like that with a constraint optimization problem. But then you have to kind of solve it in some, there's a variety of ways you can solve those constrained programs, but none of them is quite as easy as, for example, these squares. Just pops out the solution. Logistic regression is kind of an interesting case because here it turns out this loss function, or this sum over loss functions, is differentiable. So it does have a gradient everywhere. It just so happens that we can't solve for it analytically. So you can write this gradient out, and you get some expression, some function of your thetas and other parameters. But if you try to set it equal to 0, there's no way to really just do like we do with these squares and move everything that involves theta to one side and doesn't involve theta to the other side and just have the solution right there. That part is very hard to. And so you can't get this analytical solution to this function. So what do we do when something's differentiable, but we can't actually find an analytical solution? And for this, I'm going to take kind of a brief detour, but this will come up a lot in the class, so it's important to kind of become familiar with this method. We're going to use what's called Newton's method. So who here has actually seen Newton's method before, or implemented Newton's method, or heard about it actually first? Just raise a hand. Okay, most people, but some not. What Newton's method is it's a root finding algorithm. And what I mean by that is, it is an algorithm that you give it some function f. And I'm going to talk about f just being a general function now, mapping from Rn to Rn. What Newton's method does is it just finds some z such that f of z equals 0. Now, eventually, in this case, we're going to apply this where the function itself is the derivative, or the gradient, sorry. The function is the gradient. That will find a point where the gradient is equal to 0, which is, again, by our conditions, that is the optimal point for our optimization problem. But Newton's method in general is just a method for finding roots of an equation. And maybe I should draw it here, but I'll draw it here. But in the 1D case, it's a very simple update. You just say that z, this arrow means that just we set z to be equal to. So z equals z minus f of z, sorry, f of z divided by the derivative f prime of z. So why do we do this? Well, what we're doing in some sense is suppose we have some function, and I hope this is a okay one. I'm pointing out here that there are actually many possible solutions, but we're going to try to find one root. So it finds a root. If there's a function with a lot of roots, well, that can be in trouble. The nice thing about convex functions is that they only have one optimum, so there will only be, well, they have any optimum is a global optimum. So if you find a value where the gradient is 0, that is an optimal solution. So here's the intuition, what you do with Newton's method. The basic idea is you find this point here, you fit a line to it. So you have some point z, let's say z1. You fit a line to that function. Sorry, to the function at that point. Right? And that line, by just sort of definition of gradients and everything like, or derivatives and that kind of stuff, is going to be equal to f of z1, so that's just the function evaluated at that point, plus the derivative at that point times how far you are away from that point. So I guess I'll say like f hat, or f approximate of z here. Remember, z sub 1, supposed to do sub 1, superscript 1, but looks like a prime. Sorry about that. So z, there's nothing to do with power or something. It's just sort of saying indexing into, you know, a z. This equals, our approximation equals, well, just the value of the function at that initial point, plus the derivative of the function at that point. That's just the slope of this line, right? Plus the difference between, or times the difference between your point you're evaluating it at and z1. And Newton's method, what it does, all it does is say, if we're going to take this linear approximation to the function, and we're going to set that to be equal to 0. Right? So the analytical solution for this will be z equals, here in this case, z prime minus f z prime, or I keep saying z prime, sorry, f of z1 times the derivative of f of z1. Maybe okay, let me just call this z0 or something, because it is really confusing. Z prime and everything. Okay, so you just take, and that's just, you just divide by the right terms there and everything comes out. So that's saying we're going to fit a line to it, and we're going to find this point, and then we just repeat that. Remember, Newton's method basically sets this, does this again and again. So now we take a new point, we find the derivative here, we go to that, and then we're there, and then pretty quickly we converge exactly to where this turns 0. And one nice thing to say about Newton's method is that once you get close to this point, I mean, it's sort of very informally, but once you get close to this point here, you start getting to the actual point in some sense really, really fast. Formally, the number of correct digits you have of this number will double each time through the algorithm. So the number of correct significant digits will not double, but it will go by increase by some multiple. It could just be doubling, right? So that's really fast convergence. That's not just getting closer to it, or not even just getting closer to the actual true value a little bit every time, or even by a constant amount every time. You're actually doubling the number of correct digits you have every time. So it's very, very fast convergence once you get close to that point where you're near it. So for all intents and purposes, Newton's method actually will give you exact solutions to numerical precision, which is all we can really hope for anyway on a computer. This is the 1D case. People have seen this before, though, in calculus, or seen some of it before, maybe. Okay. Good. I should probably put up a little bit more basic description for the 1D case, but I think many people have already seen that before. Okay, so now what we're going to talk about in this class is the multivariate version of Newton's method. Let me just check what time it is, too. Okay, so I am actually out of time. I'll stop here because I don't want to get too much into this before the end of the class. As a preview for what we're going to do with this method is that this update I showed you for the 1D case can easily be extended to the case of multivariate functions. And we're actually here going to we're going to develop a Newton's method which is extensible to a 1D case. And all that you have here is z is assigned to z minus some derivative-like term, which we call the Jacobian, which is kind of like a gradient but not quite, times the function evaluated at that z. So it's exactly the same. It's just kind of a matrix version. This is a matrix now, so you have a matrix inverse times your function. We'll go through that. We won't derive exactly why it works. We'll just go through it, and then we'll talk about how you apply it to Newton's method. And it ends up, again, for something like logistic regression, ends up being a very, very efficient way to find the zeros, find the optimal solution to the optimization problem, even though you can't find it analytically. Okay, so we'll pick up here next time.